we are starting with Avogadro's Principle, and then we are going to take Avogadro's Principle and combine it with what we covered yesterday with Boyle's Law and Charles' Law, and we're going to create the ideal gas law and show how that works. And we're going to do a little bit of a comparison between the combined gas law and the ideal gas law, and when you use them and when you shouldn't, and that sort of thing. So we're going to start with Avogadro's Principle, where here is our piston container again. And in our piston container, we have, we'll say 10 moles. 10 moles of gas. And this piston has a it has this weight on top of it. Remember that this weight represents that weight on top of the piston represents the pressure that we're exerting on the gas and keeping that steady, because if our volume is allowed to change. If we have a piston, that means our volume is allowed to change, and so we need to maintain a constant pressure. We show this to represent a constant pressure. And so we start with 10 moles, and let's say that this this volume right here is 3 liters. What do you think would happen if we have another container here that has the same pressure on it, the same amount of pressure, but we double the amount of molecules? Same pressure, same temperature, but we double the amount of molecules. What has to happen to our piston? What's that? The piston gets bigger? Okay. The piston's going to go up, right? Okay. There's more pressure? Okay. So let's think through the concepts again. If we add more molecules, there's going to be more add more molecules to the same volume, there are going to be more collisions with the walls of the container, right? But we're trying to keep our pressure constant. I'm not adding any more weight on the top of this, which means our pressure is constant. So if our pressure is constant, then the force of the molecules that's hitting the piston has to stay the same. And that comes from the number of collisions. Well, in order to maintain that level of collisions with the top of the container, we need to allow twice the amount of moles of gas, more space, so that they can maintain the same number of collisions. Okay. So this is what would happen, and we'd have our same pressure. And to maintain the same space, our molecules are relatively spaced out by the same amount, but if we have more of them, then they have to occupy more space. And what do you think our volume would be if we double our number of moles? Okay, it would also double. So if this situation was 10 moles gives us 3 liters, this would be 20 moles gives us 6. There you go. Yeah, not squared, doubled. Okay, so it would be 6. That would be 6 liters. Okay, we'll call this situation 1, and that's situation 2. Now, if this happens, what kind of relationship is this? Almost. It's not just a direct relationship, it is direct Directly proportional. Directly proportional. Proportional being the important word on that, not just direct. Okay, so here we have a directly proportional relationship where volume would be our dependent variable and our number of moles is our independent variable. So if we change the number of moles, what happens to the volume? It goes up proportionally. All right, and the way we write this is V over N equals K, where K is the slope of the line. Okay. All right. So this again is directly. Okay. This is directly proportional. Okay, and that's the straight line. What do we call the other line? What do we call the line that looks like? Okay. Okay. The shape of the graph is a hyperbola. The relationship is inversely proportional. Okay. Get used to those words. Inversely proportional is the curved one. Directly proportional is the straight line. Okay. So that's Avogadro's principle. And to finish that out, we have, if this is 1, then we have our volume in the first case divided by our number of moles in the first case equals some constant. Okay, and that same constant is also going to equal, if we take our volume in the second case divided by our number of moles in the second case, that these two values are going to be equal. And this is this concept, because they're proportional, this will always happen. Okay, and this leads us to, and this is Avogadro's principle, that V1 over N1 equals V2 over N2. It does, doesn't it, Joseph? We have mentioned Avogadro before. Okay, Avogadro is also Avogadro's number is named after him, and Avogadro's number is the number of things in a mole, right? So it's the same guy. Okay. Kind of like we talk about kilopascals, right? Pascal it's the same as that mathematician guy with Pascal's triangle. Yeah. So mathematicians and physicists and scientists get things named after them if they were around 200 years ago. It doesn't happen so much anymore. Okay. I wish. That would be awesome to have my own principle named after me. Okay. So now we have Avogadro's principle. So here's what I want you guys to do. Or here's what we're going to do next. We're going to create a relationship between all 4 of our variables. Because right now we've used pressure, volume, temperature, and today we introduced our number of moles. Yeah? Okay, so how could we line up all of these variables? How could we arrange all of these variables and still maintain the same relationships that they have with each other? Joseph?
Could it be P1 times V1?
Let's get rid of the numbers. Just
Oh, okay. P times V over T times N.
that would, yeah. So if we arrange these, we get PV over NT. Okay, and this equals some constant. Right? So if you take all this information, if you take pressure and volume and the number of moles and temperature, and you arrange them like this, that the pressure times volume over number of moles times temperature, okay, will give you, for any gas, it will give you a constant. And it doesn't matter what these are. That's the cool thing. These numbers, once you measure them all for any gas, it's always going to give you the same constant. And I'm going to have you guys figure it out, because I'm going to bring up something from your past, which I know, Shubin, is sometimes scary for you, but okay. We bring up things from the past. Okay, and it's this. Okay, does that look familiar? 1 mole of a gas at standard temperature and pressure occupies a volume of 22.4 liters. Oh, that was a standard, huh? Yeah, knowing the molar volume of a gas. But look at what our variables are. 1 mole of a gas. That's N, right? At standard temperature and pressure occupies a volume of 22.4 liters. Oh. So, if you remember from yesterday, the standard temperature equals 273 Kelvin, and standard pressure equals 1 atmosphere. Okay, I want you guys to tell me what this constant is. You're multiplying, right? So if you're multiplying, you don't have to have like terms. No, it's not. Sorry, guys. It's me.
Yeah. It is you. It goes purple like that in the recording.
No. The record's fine. It's the projector problem. Okay, so what do you guys got? Pressure goes there. You got 0.08205. We'll leave it there. What? Here's why you don't have to worry about like terms. The units for this constant are liters, atmospheres over mole, Kelvin. Okay. This is called the ideal gas constant. And it is given by the letter R. Okay, which brings me to my favorite pirate joke. What is a pirate's favorite letter? R, you think so, but 'tis the C.
Oh, I get it.
All right. All right. So, I beg your pardon. That's a funny joke. All right. So, this is the ideal gas constant. We now have the ability to describe the conditions of a gas under any circumstances. If we know volume, temperature, pressure, number of moles, when you arrange those four variables, they will always equal this R. Now, R varies. Hold on. The concept of the ideal gas constant is constant. But because there are different ways of measuring pressure, you might see different values of it. There's another one that is 8.315 liter kilopascals mole Kelvin. Okay, and you use this if you're in kilopascals. And I think the other one is 62.4 liters millimeters of mercury mole Kelvin. Okay, all of these numbers are all measuring exactly the same situation, just with different units of pressure. Okay, so you can get 8.315 by multiplying this by 101.3. Which is, by the way, it's 101.3, not 101.5, so I told you wrong last time I mentioned what standard pressure was in KPA. It's 101.3. This times 760 gives you 62.4. Okay, so these all mean the same thing. When you convert from one to the other, you'll get these different R's. So what we use this for is we create from this we create our ideal gas equation. And the ideal gas equation is pressure times volume equals N R T. And we call this PIVNERT. PIVNERT. Okay, just as a mnemonic to remember the ideal gas law. PIVNERT. So, like, look at the letters. PIVNERT. Right? PIVNERT. All right. Well, oh my gosh, you guys. Okay. This is how to say the mnemonic that represents PV equals nRT. PIVNERT. PIVNERT. It is, I don't know. It has been the standard mnemonic for remembering the ideal gas law for generations. So, this brings us to, two things. One, we now have two gas equations. We have the combined gas law, which, by the way, we can derive the combined gas law from the ideal gas equation. We have PIVNERT here. If we are going to study how a gas changes when we change certain variables of it, so if we change the pressure of a gas and we change the temperature, what is its volume going to be, that sort of thing. But we're not changing the amount of gas we have. That leads us to this, that if these two are constant, right, NR, if the number of moles and well, our ideal gas constant is constant, but our number of moles is also constant, then we get this relationship, this PV over T. And so if we have two situations, then we would have a before and an after situation for a change, and we take these two and set them equal to each other, and we get our combined gas law. P1 V1 over T1 equals P2 T2 over T2. And so we can derive this from our ideal gas law. So really the only one you ever have to know is the ideal gas law, but it helps to remember this. We use this, and I mentioned this yesterday, we use this when we have a changing situation. This is an equation. This is an equation of change when you have variables that are changing with your gas. This is an equation of status. So in other words, if you don't have a situation that's changing, you're just going to describe the nature of the gas that you have. You're going to use this equation. All right? And so I have an example of that for you guys. My example is it's our R in a chute. 2.7 liter sample at 0.56 atmospheres. Okay, so how many moles of a gas at 300 Kelvin are in a sample at 0.56 ATM. Okay. I leave this to you guys. Okay, so what you need to do is you need to identify, first of all, is this changing? Is there a before and an after situation with this gas? No. Would we use our equation of change or our equation of status? Our equation of status. What is the status of the gas? What is the gas like? So then we have PV, N, R, and T that we need to identify. We always know what R is. That's our constant. We always know what R is. It is 0.08205. That's the constant. That is the ideal gas constant. It doesn't change. Okay. So how many moles of gas? We don't know that one. 300 Kelvin, what's that? That is our temperature. 2.7 liters is our volume, and 0.56 atmospheres is our pressure. So if we're looking for our number of moles, we solve our equation for moles. So we're going to divide by R and T to get N equals PV over RT. And then we substitute our values in. 0.56 atmospheres times 2.7 liters over 0.08205 liter atmosphere mole Kelvin and 300 Kelvin. Sure, or it's 821, that's fine. But notice what cancels. This is our ideal gas constant. We on the previous page. Okay. All right. So then you multiply across the top and divide by everything on the bottom. Notice that your units of ATM cancel, your units of liters cancel, your units of temperature cancel, leaving you with 1 over moles in the denominator, which means moles is in the numerator. So that will be your value. And this winds up being, when you plug it into your calculator, which I recommend you all do, this winds up being 0.0614 moles of gas. Okay, couple of administrative notes for class. When you are working through this and you write the ideal gas constant, I will deduct a point from your work if you do not include all of the units in the ideal gas constant. Every single time. Every single time. So if you go through your whole work and you just use that number without writing down that, you're losing a point on that problem. Okay. On that happy note, that's it for the lecture, and I'll take questions after this.